What I'd like to talk today is about some of the work we've done to develop what we call digital chimeras or virtual chimeras. And I'll try to explain a bit why we're doing it and also what the concept is and some of the methods that we've developed to that. So the reason that I'm working in our group on this topic is because we want to address a problem that we see in nowadays, which is that despite all the work that has been going into regulating medical devices, we still have a massive amount of impact and risk on patients, both on account on studies in the US, but also in the UK as well, in what is known as the Cumberland report. And this has produced a lot of pain and suffering in a lot of people over the last few years. Now, some of the recent papers I have looked at and meta-analysis on failure modes indicate that the top 5 reasons why devices are being identified as root causes by FDA have to do, the large majority of the class 1s are related to device design. So this is a 53% of 43 studies and about 30% on nearly 200, which are not just class 1 but broader classes. So the problem is fundamentally on the design space. And this is a slide that we sort of co-created with Mark Palmer, where fundamentally what it shows that if you look at the different the life cycle of a product across the R&D process from the discovery all the way to the post-marketing evidence, and if you look on the y-axis to the number of problems that you need to fix in a particular design, what we tend to do at the moment is basically this dotted line here. So we tend to freeze very soon the design space of our products because if you are a startup and you need investment, you need your push to generate evidence of some sort, and it's expensive to do that. So you try to freeze your design, and then as you go through other phases, you start figuring out everything that can go wrong and starts appearing. And the deeper you go into this pipeline, the more expensive it is to go back to the drawing board and fix sort of the unit problem that you detect. So if we could somehow turn this around and find some cheap way to do much more thorough testing early on, this would lead to much more safe products, hopefully, but also a reduction in cost for testing. You will still need to do trials, but the idea is that they will be more confirmatory of your hypothesis rather than sort of trying to assess fully the trust. Now, this boils down to, if you look at any clinical trial, human trial, one of the most expensive parts of it is actually recruiting patients. So it's not surprising that creating virtual populations is an important part because what we're trying to replace is that part, right? Now, over the years has been a number of, if you would have looked into a number of years ago, digital twins were very simplified models, and then people who have developed, full families. But this is always very laborious and, very expensive time-wise, and it still doesn't give you a lot of variability. One of the things that we are working in the lab as part of ERC Advanced grant that I got last year to work in this topic is we got access to a randomized controlled trial data set that we're trying to what we call reenact. So essentially generate a digital twin for each of the patients in that study and then create a full simulation for every single subject. We've done this in the past with neurovascular devices, but there we didn't have the access to the original data. What we could demonstrate is the equivalence at group level on the performance of the real versus the clinical, the virtual trial. What we want to do that here is by looking at case by case. But just to give you an idea about the magnitude of the impact here, so this particular device was taken out of the market about a few years ago. The trial itself cost about 80 million, and the losses just due to the recall of the device was between 200 and 300 million. And this is just one device, this particular device, but you have all of these plethora and a larger zoo of devices, all to do the same thing fundamentally. So if for every aspect that we're trying to cure, we need to go through every company, going through all of the different steps that I mentioned before, this is just completely unsustainable. Now, if you want to do digital twins, one of the things you can do is you take each of the data sets and then you sort of create your 3D model, build a model, in this case of the valve that we are interested in, and then eventually you sort of put together a simulation pipeline like we were discussing during these last 2 days. This is something we are working at the moment. We've done all the analysis on the nearly 700 patients on the study, But what we're also starting to look is, can we actually do better than that? Can we create virtual populations where from those populations we can derive the same learnings that from this trial that was so expensive and time-consuming? So this diagram tries to explain the difference between twins and chimeras as we sort of define it ourselves. So in the upper part, what you have is a study, say a randomized control trial, where you have N subjects, you give a particular therapy, and M you give the other one. And twins would be taking each of these subjects and create a digital replica of all of those. So if you have 1,000 patients in your trials, you will only have 1,000 patients twins. And you haven't solved the problem of much more thorough testing that I was talking about. So if you look at this, this plot, which shows variability, so the envelope in anatomy, the envelope in operational, physiological and operational variability of the device, and the device themselves, I tend to think this is a Gruyere cheese, which is full of holes where we don't have a lot of data in it, right? So we only have a few very, very sparse samples. What we would like to have is something which is like this, where every black dot corresponds to a measurement point, potentially. Now, the other problem that you have if you try to do the thing about is that, I'm sure all of us have experienced that, it's almost impossible to get a data set where you have everything you want for every subject. Because the reality is the healthcare system and even the trials don't work that way. You don't collect everything and then you ask yourself questions. You collect data as you need to make clinical decisions. But what it is a lot easier to find is to find databases where of some people you have lots of imaging, of some other people you have lots of wearables, and other people you may have, I don't know, other type of information, environmental information. Now, if you're lucky, you can get all of these different data sets from the same region or country, which means you have the same population, but there are different samples of it. So the idea of a chimera is the idea of building a blending model that combines the data that comes from all of these different sources into a generative model that you can actually sample from it and generate potentially as many subjects as you want. Okay? So you solve a number of problems, the limitations of numbers, but also, if you think even this from a GDPR point of view, here you have potential traceability all the way to the end of the identity of patients, while here you break it very early on because you created a statistical blending. Now, that's why we call them chimeras, because what we're trying to do is combining data from a number of sources. Now, what is important is that one doesn't lose the idea that you can have multiple samples, but they need to be from the same population. There has to be something that brings them all together. Now, another way to think about this problem, if we look at another part of the problem, is that sometimes you may have, for a particular organ, say we want to have a very detailed model of the heart with the valves as well, you may have maybe MR and CT from one group of patients and then echo probably from a lot of those, where you have a lot more information about valve and valve dynamics. But again, you need to piece it all together, and they may not be from the same subjects. There may be samples from the same population, but not necessarily paired, all these data sets. So basically, the concept is, say that you have two databases, and each of them has a certain structure missingness in it. So some of these data sets contain parts of the same organ or different parts or different pieces of data, making these parts of the same organ for simplicity here. And then can we develop some sort of machine learning techniques from where we can synthesize a single model from everything? This is not just anatomical registration, it's a statistical blending as well. And from that model, you then synthesize a library of anatomies that you can use to do the device testing. So that's, so what I'm going to do now is I'm going to summarize a bit the ideas behind this paper that was published a few weeks ago, where we sort of provide the very first version of our framework to do that. But fundamentally, what we're trying to learn is a statistical joint latent space from where all of these different parts are, again, statistically integrated, and then sort of synthesized from it. So there are two ways to do the blending. You can say that you have channels, and these channels correspond, say, a channel may be the ventricles and another channel may be the atria. Imagine, because you got them from two different sequences of MR or from two different imaging modalities. They are not necessarily pairs, so this is not John and John, but this may be John and this may be, Louis. They come from the same population, but again, they are not necessarily paired. So you can either create models for each of the parts and then have a synthesizer for each of the subdomains, or you can actually have a joint lattice space built with, you can do this with variational tone coders and this with multi-channel variational tone coders. Now, I'm not going to explain the details of exactly how we do it, but you don't need to have imaging channels only. You can also have information that has to do more with demographics of the patient. Is it the sex, the age, and other variables. So there is a first part where you do what we call the part-aware generators, and then a second one, there is a network that does the composition of all of those. These generators, we will see a bit through the experiments that the independent generator gives you more expressivity than the joint lattice space. However, the joint lattice space gives you more specificity, and it's a bit of a trade-off between these two. These two ways of doing things, independent generators or dependent generators, is fundamentally down to the way you build the reconstruction loss. So the overall loss is some reconstruction loss, a loss that has to do with the statistical distribution, so a Caronin-Loeb or Kurbach-Leibler type of divergence, and then a regularization cost that I'm not going to spend lots of time in it, but it's based on some sort of a smoothing terms. In the case of the independent synthesizer, what you're doing is that every channel every output tries to reconstruct as best as possible the input. While in the other loss, every output needs to be the best possible prediction given all the inputs that you have. Okay? This also gives you another advantage. You don't need to have all the inputs for every sample as well, which is the way in which we deal with incomplete datasets as well. So what you're trying to learn is this joint lattice space by these multiple vistas that you have. So you consider every channel like a different vista. Some details about the implementation. So all of these encoders and autoencoders are graph-based encoders and autoencoders, and they have a number of advantages, and they're also multi-resolution representations, so you can have quite a fast and efficient way to implement this. And then finally, I also mentioned that there is a compositional synthesis. What a compositional synthesis does is it takes the joint lattice space and reconstructs back the different parts, and then we have two different losses, one that ensures that there is the best alignment between them rigidly, and then there is a second one that does actually the smoothing over the edges, so it sort of adapts the deformations around the edges, because they don't necessarily need to be perfectly fitting to each other. So this is done by minimizing distances in the second part of the synthesis. Now, let me give you some keys about the experiments that I'm going to show in a moment. So we took UK Biobank, where we have full heart, so we have all the parts of the heart, and therefore we can create synthetic data sets that have only parts of the heart to actually demonstrate that we can build having a gold standard. So we have 5 parts in the heart that have been landmarked, about 2,300 subjects. The other aspect is we use about 400 of them for training, 59 for validation set, and about 1,800 for test set. We looked at 2 different types of experiments. You will see experiments that I say complete or full overlap. They are when you have all the structures for all the subjects in the training set, but we also have partial overlap. And what we did is we had 300 cases of the 422, of which we took randomly one of the structures out, as if that is missing from our experiments. And the remaining 100 plus had all the parts in it. And then we did a number of trainings and testing, and I'm going to show the results. All the experiments are done in end-diastole, but you can do the same thing for every section. This is the sort of synthesis you can produce from those. So what we show here is that, so how you validate that? So you have the dependent and independent generator, and then whether the experiment is with a complete anatomy or complete coverage or partial coverage. This is the results if you use a standard PCA as a reference, and these are for the different chambers that we looked at. And what you see is that if you use dependent generators, your generalization is best using the independent generator, while the dependents have a larger error. How do we measure the errors? We measure it with the Euclidean distance between the different nodes, or using the F1 score that has to do with the precision of the reconstructions. So you want lower Euclidean distance and higher F1 scores in all these experiments. And then we also looked at the specificity. So a specificity here for the different models. They are now here in rows rather than in columns. Again, specificity is the Euclidean distance. What this means is we synthesize a new subject and we look at the closest one in our training set and we compare the distance about this. This is that if you generate something which is a complete outlier, you will get a very large error in doing so. Okay? And in this case, you tend to get better. So this is a measure of are you generating plausible shapes or are you generating something completely crazy. And then finally, the other thing we looked is at the clinical relevance of these measures, and we define a measure called clinical acceptance rate, which is the percentage of the synthesized samples in the virtual cohorts whose cardiac indexes are within 90% confidence interval from the real ones. And you can see that most of the errors are in the 96, 98, 99%, so it's actually quite good. This is kind of the same thing, but shown now for a number of parameters for left ventricular volume, right ventricular volume, and atrials as well. And what you see here is the UK Biobank reference value. So this is the gold standard. This is what the mean values and the variation are with use PCA or any of the other techniques. And we believe that these are the ones that tend to work the best in most of the cases. You see you have ranges which are closer to the UK Biobank than PCA and not that many outliers in comparisons with some of the other ranges. So limitations of this work, you need to have a fixed topology. So this doesn't work for arborescent structures or for when you have, for instance, congenital changes like the ones that David was talking yesterday from some of these kids that are born with transpositions and others. We cannot ensure the topological, in principle, we haven't observed that, but there is no guarantee of topology. We don't have conditional generation, and also, although we have shown how to do multi-source data federation, we are at the moment working and doing some much further experiments. Now, something that I'm going to show only 2 slides, so I want to bring the talk to a close, but is we've been progressing as well, and there is a paper in Mika last year of where we do controlled synthesis. This is so that you can actually start putting inclusion and exclusion criteria from trial as part of your synthesizer. So you can say, well, it's not just that I want to synthesize people, I want to synthesize males between 45 and 65 years old, for instance. And you can do that based on this other extension that we did. And what we are doing at the moment is working how to validate the synthesis compared to a specific cohort. So we are talking UK Biobank, Synthesise, generating a model with that, then putting the inclusion and exclusion criteria of this randomized control trial that we have access to, and trying to recover the parameters from the randomized control trial population. If you do that, you also have the ability to then synthesize chimeric scenarios. So, well, sorry, this is just to show a number of parameters, but for instance, you can change the weight of the patient and look at how some parameters will change in those sort of counterfactual scenarios, in a sense. So in summary, I hope that I have enthused you to the idea that we need to do something about the way that devices are produced, and that perhaps with these chimeric populations we have a way to deal with some of well, for generating very extensive data sets. The idea of that we're working on, I think, is quite important on incorporating inclusion and exclusion criteria. And another thing that we're working at the minute, and sorry for the incomplete sentence clearly there, is in finding ways to do certification of models, so that actually you can build a model saying, I know that to a 1%, with a probability of 99%, I'm going to be equivalent to the target population that I am aiming to. And there are ways to do that I haven't presented, but that's where we're focusing at the minute. Thank you.
Is there time for one quick question? Yeah.
Yeah, this is really a key issue in in-silico clinical trials and how to sort of create these synthetic populations. How do you anticipate applying this framework to disease patients, particularly where there's anatomical features that are linked to one another? Have you guys started to sort that framework?
If there are...
Yeah, where you're not creating normal anatomy. Left atrial dilation, left ventricular dilation,
think there are two parts in that question. One is, can you synthesize pathology? And the other one is, can you synthesize pathology that has fundamental topological changes with respect to the normal? And I think the answer to both is yes. So the first one is more a matter of how you balance your training set. The second one, it requires methodological changes. So going from the sort of models we work to more sort of diffusion techniques. And those can synthesize multimodal distributions. And effectively, each of the different topological alternatives is like a different statistical mode. But you need to have nonlinear ways to represent the statistics so that you can jump into each of those, right?
Okay, if there's any other questions, you should probably keep them for the coffee break. Good, thank Alex again. Great talk.